Hello guys, welcome back to another tutorial. Hit the bell icon button so that you don't miss out any tutorial.
IoT device architecture course. In this lecture we're gonna have a look at the hardware and the software implementation of a simple IoT project. So in this lecture we're gonna have a look at the big picture of an IoT project. What are the hardware? What are the typical hardware of an IoT project? What is a typical software? How do we integrate between the software and the hardware in an IoT project? So this is the agenda for this lecture and for the coming lecture. Probably is gonna be divided into two lectures. So we're gonna start by introduction to microcontrollers. What are the microcontrollers? Why do we use them? Why do we even use them? Should we use them? Do we need them? Etc. And then we're gonna have a look at the applications and the types of microcontrollers. And as an example of microcontrollers, we're gonna have a look at the basic structure of the ATmega16 microcontroller. And then we're gonna head to the Arduino platform. Why did I choose Arduino platform? Because Arduino is the most famous and the most supported microcontroller development board available. So it is very easy for beginners and for makers to start developing their own IoT projects using the Arduino platform. And then we're going to have a look at the Arduino specifications and features. Then typically a project consists of sensors and shields. So we're going to have a look at the Arduino sensors and shields. Then as an example of other microcontroller boards, we're going to have a look at the ESP8266 node MCU board, ESP32 based board, and then as an example of an IoT project, we're going to have a look at an IoT project end-to-end, basically developing the hardware and the software, connecting it to the cloud, and then seeing the results through the dashboard. So we've talked about this layer. This layer is the things layer, is the sensors layer. This is where the devices communicate with the sensors, gather data, and calculate and gather the needed information and data. And then this is the communication layer, and we've talked about this architecture in more details. But what I'm concerned here is that in this session we're going to cover this layer. So what are the microcontrollers? What are basically the devices that gather this information? What are the sensors that we should use? How do we write software for these kind of devices? All of these stuff. So let's start by the very basic question. Why should we even use microcontrollers? Why should we learn how to use and program microcontrollers? So a long time ago, projects and electronic circuits electronic circuits were designed using discrete ICs. So for example, if you're developing a clock, for example, you need a timer IC that keeps track of each second, and you need an LCD, for example, that prints out the current time in terms of seconds, minutes, and hours. So this design that consists of a timer IC, so the IC is basically, it does only one thing, just keeping track of time. And then there is, for example, another IC that is responsible for the LCD, and another IC for crystal oscillator. But the thing is, when you finish this design, it's a fixed design. So if you need to edit the design, you're gonna have to go all over again through design. If you need to test this design, if you need to basically any step that you're gonna do in this project would involve actually designing from scratch and developing from scratch the project. This is where microcontrollers shine, basically, because microcontrollers replace all the hardware hassle with the software. So for example, in our clock project, you basically tell the microcontroller in instructions that you're gonna need to keep track of time, you're gonna need to communicate with the LCD display, and you're gonna need to display the current time through this LCD. So if you need to test this device, if you need to redesign this device, you're gonna have to just rewrite this code. You don't have to redesign the hardware. You don't have to go through all of this hassle again. So in brief, if you need to make any change to the functions using discrete ICs, you would have to go through the schematics, welding and wires, and this job was typically only done by electronic or electric engineers because of the huge technicality involved in welding, in designing ICs, in figuring out the data sheets of these ICs, all of this information. But thanks to the integrated ICs, we now have microcontrollers. So microcontrollers use software, they use code and instructions to carry out functions. Instead of having discrete ICs for each function, you just have to write the specific instruction that you need the microcontroller to execute. So in the end, microcontrollers enables faster development, testing, and debugging. So now we know why should we use microcontrollers. Basically, microcontrollers enables us to make prototypes and develop prototypes faster. They enable us to test and debug and redesign and reiterate on our projects and prototypes in a more fast and more efficient manner. Let's now have a look at the applications of microcontrollers. What are the microcontrollers used in? So the microcontrollers are intended for embedded devices in comparison to the microprocessors, which are used in PCs and other purpose devices. So basically, this is the difference between embedded systems and general purpose systems. The PC that you're using is a general purpose system. Basically, it is designed to execute a lot of tasks, wide variety of tasks. But an embedded system is designed to execute a certain task in the most efficient way. So typically, microcontrollers are intended to be used in the embedded systems, in contrary to the microprocessors, which are used in PCs and other general purpose systems. Microcontrollers are employed in automatically managed inventions and appliances, like power tools, implantable medical devices, automobile engine control systems, office machines, remote control appliances, toys, and many other embedded systems. So a typical example of a microcontroller would be light sensing and controlling devices. For example, we can connect a sensor that is called light sensor. It basically senses how much light in the environment, and then we can control a certain lamp or a certain switch depending on the value of this light sensor. Or we can have a temperature sensing and controlling device, fire detection and safety devices, industrial control devices, such as the industrial instrumentation, process control devices, and even in the measuring device. So any freshman that is going to study electrical engineering is going to use avometers. It's going to use devices that measure the current, voltage, and the resistance of some elements in the circuit. So these devices also employ microcontrollers during the measurement of these values. Okay, so we now know why should we use microcontrollers. What are the applications of microcontrollers? Now, what are the microcontrollers? What do they consist of? So what is the microcontroller? Microcontroller is compressed microcomputer, simply. It's manufactured to control certain functions of an embedded system, be it in office, in robots, in home appliances, in motor vehicles, and a number of other gadgets. A microcontroller comprises of components like memory, peripheral, and most importantly, a processor that is a central processing unit. And we're going to have a look at the more detailed structure of a typical microcontroller. Microcontrollers are basically employed in devices that need a degree of control to be applied by the user of the device. So let's have a look at the basic structure of a microcontroller. What does the microcontroller consist of? The basic structure of microcontroller comprise of the most important element or component of the microcontroller is the microprocessor, or the CPU, the central processing unit inside the microcontroller. The microprocessor is the device which is employed to fetch instructions, decode, and execute the instructions. So this is the main functionality of the microprocessor. The microprocessor basically fetches the instructions from the memory. That means getting the instruction or identifying the right instruction, and then decoding the instruction, figuring out what does this instruction mean in terms of functionality, and then executing this instruction in a continuous manner. With the help of CPU, all the components of microcontroller is connected into a single system. So basically the CPU is the heart of the system, because the CPU accesses the memory to fetch the data. It uses other types of memory as a RAM to use variables and all other kinds of stuff. And then when, for example, if it decodes a certain instruction that is related to a certain functionality, it's going to go to this intended IC and execute a certain functionality. So the CPU is the heart of the system. Instruction fetched by programmable memory is decoded by the CPU. So that's the microprocessor. And then we have a memory. Memory chip stores all programs and data. In a typical microcontroller, we have two kinds of memory. We have ROM, which is read-only memory, and then we have RAM, which is random access memory. We typically use ROM to save the code, that is the instructions that the microcontroller is going to execute each time it basically wakes up. And then we use the RAM, which is the random access memory, to handle all kinds of memory requirements needed by the code itself. For example, if your code have variables, if your code have structures, if your code have functions and stack and other kinds of really technical details, it is going to be used inside the RAM. The main difference between the ROM and the RAM is that the ROM is typically read-only memory. So it is the instructions are saved whether there is a current supplied to the microcontroller or not. So it's basically non-volatile, which means that if the current is cut off from the microcontroller and then wakes up again, the code is still there. It can still execute the same instructions. Okay, so this is the microprocessor and the memory. Now let's have a look at the input-output ports. So each microcontroller needs to control other sensors. So each microcontroller basically needs to get data from other sensors and control other devices. This is typically done through the input and output ports. I/O ports are basically employed to interface or drive different appliances, such as printers, LCDs, and LEDs. So for example, a microcontroller might be able to get a certain data from a sensor through a pin and then control a light switch through another pin. And these kind of operations are related to the input-output, so that's why they're called input-output ports. Then we have serial ports. Serial ports give serial interfaces to the microcontrollers. So for example, back in the old days, they had a PS2 port. That is the very old mouse cable or the mouse interface. In that's way before even they invent the USB standard. So serial ports in general give access or give connectivity to the microcontrollers to other devices. So if you want the microcontroller to be able to get, for example, information or get data from a mouse, for example, a very old mouse that uses some parallel port mouse or a serial port or a PS2 port, it's going to use a serial port in this function. Another basic component of a microcontroller are the timers. So typically microcontrollers run on clocks and run on oscillators. So we need a certain block or a component to keep track of the timing of each instruction and the timing in general. So a microcontroller may be inbuilt, that is built in it, one or more timers or counters. Typically, we might use the timers to keep track of time, and we use the counters to count a certain events, for example, pulses, or for example, amount of signal or amounts of data that is being given to the microcontroller. So, timers are employed to count external pulses. The main operations performed by timers are pulse generation, clock functions, frequency measuring, modulation, and making oscillations. And the basic structure of a microcontroller has much more information than what we are covering here. We are merely covering the very basics of the microcontrollers. But in a typical, for example, AVR microcontroller course, you're going to handle all of this information. The timer, the serial, the input output, the microprocessor, the instructions, all of this stuff is going to be handled in much more detail. In this session and in this course, we are covering the basics and we're giving the overview of the system or a typical IoT project. Another component in the microcontroller is the ADC, which is the analog digital converter. ADC is employed to convert analog signal to digital ones. The input signals need to be analog for ADC. The digital signal production can be employed for different digital applications such as measurement gadgets. We need the ADC because the external world of the microcontroller is being driven by analog signals. So typically there are two types of signals, digital signal and analog signal. All the microcontrollers and the microprocessors and the microcomputers and all of the electronics are driven by digital signals. But the world is not governed by this digital signals, they are governed by analog signals. So we need analog digital converters to basically, for example, convert the analog signal of a voice of someone to a digital signal so the microcontroller can handle its information. Then there is the opposite, which is the DAC, which is the digital to analog converter. If we want to, for example, to have output or to output an analog converter, we can use some sort of a DAC to handle this kind of process. So this converter executes the opposite function of the ADC, which is that the device is generally employed to supervise analog appliances like DC motors, all of that stuff. Then a very important, let's say, concept in microcontroller is the interrupt. So the interrupt control is used for providing interrupt for a working program. The interrupt may be external, that is activated by a certain sensor or a certain action through the interrupt pin, or internal, using the interrupt instructions during programming. Okay, so now let's have a look at an example of a microcontroller and have a look at the structure of the microcontroller and how does this structure map to the basics that we've talked about. So for example, if we take a very famous, very supported microcontroller called the ATmega16. So what is the ATmega16? So this is the microcontroller that we are talking about. This is a single chip computer that comes with a CPU, a microprocessor, a ROM that handles the instructions and a bunch of other functionalities, RAM, a different type of memory, EEPROM, a different type of memory, timers, counters, ADCs, and 4-bit ports that are the input-output ports that we've talked about. They are 4 ports, port A and port B and port C and port D, where each port consists of 8 input-output pins. So what's the structure of the ATmega16? The ATmega16 consists of a CPU that we've talked about, flash memory, SRAM, and EEPROM. These are all different kind of memories that each one serves a different functionality. Timers and counters that basically handles timing events and counting internal and external events. UART is a serial protocol that is used in communication between microcontroller and microcontroller, and that also can be used to communicate the microcontroller with a PC or any other device for that matter. So it's a communication protocol, just like the two-wire interface, just like the SPI. So the UART two-wire interface and the SPI are three communication protocols. They enable the microcontroller to handle information between other microcontrollers or other devices and sensors in general. Then we have an ADC that we've talked about, interrupt unit that we've talked about. Watchdog timer is a different type of timer, but we're not going to handle the details of it right now, just for not to confuse anyone. Then we have the microcontroller and timing, internal oscillator, and the input-output ports that we've talked about. So this is the internal structure of a microcontroller. Typically, it's the ATmega16 architecture. Okay, so what are the types of microcontrollers? So does the microcontrollers differ, or what is the difference between different kinds of microcontrollers? So microcontrollers are divided into categories according to their memory, architecture, bits, instruction sets. So let's discuss the types of microcontrollers. So for example, there are, according to bits, there are 8-bit microcontroller, there are 16, so this is 16, this is a typo, this is 16-bit microcontroller, and then there are the 32-bits microcontroller. So the 8-bit microcontroller executes logic and arithmetic operations on 8 bits. So for example, 8-bit microprocessor is an Intel 8031 or an 8051. So what I'm saying in this slide is that basically there are three kinds of microcontrollers. There are 8-bit microcontrollers, 16-bit microcontrollers, and 32-bit microcontrollers. So 8-bit microcontrollers mean they handle information in terms of 8 bits at a time. It's the address bus and the data bus of the microcontroller is 8-bit wide. The 16-bit microcontroller operates on 16 bits at a time. An example of 16-bit microcontroller is the Intel 8096. And the 32-bit microcontrollers require 32-bit instructions to carry out. So basically, the operations and the instructions are operated or are executed on 32 bits at a time. So these are different kinds of microcontrollers in terms of bits. Let's have a look at different kinds of microcontrollers in terms of memory. So there are external memory microcontroller. They are typically used with a micro. So when an embedded structure is built with a microcontroller which doesn't compromise of all the functioning blocks, it's named as external memory. For example, the 8031 microcontroller uses an external SRAM to fetch the instructions from that memory. So some kind of microcontrollers don't have memory to save the instructions, and for the processor to fetch those instructions, it's going to need an external memory for that function. And there are other types of microcontrollers that have embedded memory in them, and this is the more typical kind and the more used one, is that the microcontrollers have their own memory embedded inside them. Then there are different kinds of microcontrollers in terms of instruction sets. So there is a CISC, which is the complex instruction set, means complex instruction set computer. It allows the user to apply one instruction as an alternative to many simple instructions. And then there is the RISC, which is the reduced instruction set computers. So the RISC means that the operation time by shortening the clock cycle by instruction. So in simple terms, what is the difference between CISC and RISC? What is the difference between complex instructions and reduced instructions? So the methodology behind complex instruction is that we're going to make instructions that execute complex commands. So for example, that's merely an example, but if you want to multiply certain values in the registers, in the CISC we can have a multiple. So we can have an instruction that executes this functionality in one instruction. But in the RISC, we're going to have 3 or 4 instructions. Each single one instruction in those 4 instructions is simpler, but the 4 of them at the end they execute what a single instruction in the CISC executes. So the reduced instruction set means that each instruction is reduced, is more simple, but you're going to need much more instructions to execute the same command or the same output that a single instruction from the sys can execute. And then there are different kinds of microcontrollers in terms of memory architecture. That is, for example, there are Harvard architecture and there is the Princeton memory architecture, the von Neumann architecture. And like in a typical microprocessors course, you're gonna handle a lot of information regarding the difference between the Harvard memory architecture and the von Neumann memory architecture.
Thank you for watching. Don't forget to subscribe to the channel. If you like the video, do give us a thumbs up and share it. Also check out amazing discounts and offers on our premium courses in the description below.